So we are going to talk about presenting data today. So I'm admitting some more students. I think there are some internet connection problems at the moment. So we are going to talk about presenting data, and we are mostly going to focus on presenting as presentations, oral presentations, and we are going to also talk about graphs, preparing graphs as such. So going a bit generally and then also technically and practice. So today's lecture resources, two that I would like to share with you. There are enormous amounts of resources, how to prepare graphs, how to prepare presentations. One that is freely available is, I don't think you see that when I show it to you like this, right? Is a EPCC visual guide, which is meant for communicating climate change related research results by scientists to different other sources. So this guide focuses both for how to communicate to other researchers, how to communicate to policymakers, and how to communicate to general public. It is less how to communicate to other researchers, but more how to communicate to general public and to policymakers. And this is freely available from this link. The slides are not yet up in Athena, but they will be after we finish. And as it is freely available, it's quite good material. You don't need to buy as it as a book or anything, but it is a book. It's 24 pages. I think about an hour of reading. It has quite some pictures to also explain the points that they are making. And in addition to this, when you get interested in presenting data and you want to learn more, read more, dig deeper, then the book that I love most is by Cole Nussbaum McNaplick, which is, I think it's originally from 2018. And even though the name says that it is storytelling with data for business professionals, then it is actually also used for absolutely anyone who is communicating data. And in analytical chemistry and in chemistry in general, the big part of our work is about obtaining results, which are often numeric results, and communicating these numeric results to other parties. If we do our measurements and we don't communicate them to anyone, then there isn't much of the use of the data. It doesn't make sense to make the measurements if no one finds out about them. Okay, so these are the resources that are used in here. Okay. So now when we start preparing to present our data, then there are two basic questions that we need to ask before we even start preparing anything. We have collected the data. Let's assume we have our data at hand. And the first question is, whom are we going to present this data to? So what is our audience? Who is our audience? In the most broader sense, we can divide them into popular science audience. So for example, if we submit our data to a local popular science newspaper column, but they can also be peers, meaning that they are people who know what we are doing, so they have maybe a bit more pre-knowledge. And it can be also experts, for example, conference presentations, or in your cases, for example, when you are going to do your bachelor thesis or later master thesis, then you communicate also your results to experts, but you have to probably keep in mind that they might be not exactly on your topic. So they might be experts in the field, they might be experts in analytical chemistry, but they don't know exactly what you did in your work when you were working in the lab. So this context is quite important for knowing how to present. So when you know who you're presenting to, then we kind of need to understand what is the language that they understand and what is their pre-knowledge. So from the pre-knowledge point of view, do they know this topic very well, or don't they? Maybe they don't know this topic at all. What is the language that they understand? Can we use our analytical chemistry terms? Can we start using reproducibility and repeatability and assume that the person makes difference between reproducibility and repeatability? Or do we have to use something more generic and first explain this term? So when you would present to me, then you would probably assume that I know what is the difference between repeatability and reproducibility. But if you would be presenting to a professor in physical chemistry, then maybe you need to put a reference about what is the difference between these. And if you would be presenting to a column, a popular science column in Expressen, then you would probably need to explain a bit first, what is this reproducibility and why is that even important? So this sounds all very logical that we need to think about it, but unfortunately too few presentations are being designed by first thinking about the audience. And this is where often things go wrong, in the sense that there very often is too little background. So the people in the audience are lost because they don't have the pre-knowledge that the presentation requires. And sadly, this also happens on scientific conferences quite often. You would think that you present to experts, but often people forget that these experts are experts in the field, but not precisely on your topic, not precisely on these measurements that you have been doing. So this background quite often gets lost due to this. So this is basically the first thing that I would suggest you to start thinking about when you present. And this also is when you present in the courses. If you present to your students, then it's a bit different than when you present, for example, in your defense of your bachelor or of your master thesis. So the audience also defines what kind of visualization we can use. So what types of graphs the audience is used to? Is it that they understand very complicated graphs, or is it that they are mostly used with very basic line charts, for example? And also the field defines a bit what kind of graphs they are used to. Because for example, I think the simplest difference in chemistry would be between analytical chemists and biochemists. So biochemists, for example, use very much box and whisk charts, maybe charts. Maybe you have seen them also in the biochemistry course as well. But analytical chemists almost never use this kind of charts. So you would need to know what kind of charts and what kind of visualizations the people you are communicating to are used with. And of course, it's very important to know how long time do these people have time to look at the data. So when you do a presentation in your of your thesis project or your research project, then probably you show each slide for 30 seconds to 4 minutes, probably not longer. But if you present or send your work to Expressen, then it is printed on a page and a person can look at this half an hour when one finds it interesting. So there is immensely more time to focus on the content of the graph. So these are basically the important aspects in knowing who is your audience. Do you have any questions in the meanwhile? No questions. Okay, so I show you a graph here. This is not chemistry related, but I found it quite good as an example in here, in the sense that this is level of freedom and democracy in Middle East and North Africa, sorry. And this looks pretty fancy. My question to you is, what do you think whom this graph and under which circumstances it is meant for? The content doesn't matter, just look at the presentation of the data. Maybe the first thing would be, what do you think? Is that for printed communication, or is that for presenting in an oral presentation as a background slide?
Print, I think, because you have to have time to read all the.
Yes, so the opinion is that it is for printed media because there is a need to actually read the text. It's not the point of the graph doesn't pop out from the graph immediately. Any other opinions? Maybe about expertise level?
Easier because it's not like detailed in what it is. You just have like a scale for political and civil liberties, and it has just made a number system of it on each line. So it's not that complicated.
Exactly. So the content has been simplified significantly in the sense that it is just 3 levels. It's not free, partially free, free. There is not any, it is not in a detailed way explained. What does that mean? What are the aspects? Is it now the journalism? Is it that voting? What are exactly the parts that are combined into these levels? So from this part, it is simplified, but at the same time, it is quite rich in content. So probably it is for general audience, but for real reading, not for looking at on a presentation, something like that. Okay, questions or comments? No. Okay. So now when we know whom we are presenting to, then the second question would be, what do we want to say? So this is actually something where some people say we first should think what we want to say and then who we want to say. But basically, these are the 2 things you need to think always about. So it doesn't really super much matter which one do you start with. But the second thing is, what do you want to say? And again, I must emphasize that it is too often that people don't think what they want to say. They just do the presentation because they have some measurement results and they just put everything there without understanding what they want to say. And this is where presentations get too long, too detailed, and are hard to understand. And the same about the graphs. And it's not only that the content depends on what is your message, but it's also the form that depends on your message. So for example, on this slide, we have two different graphs for communicating the same results. So we have compounds ABC, and we have methods 1 and 2, and we have measured a property, a recovery, for example. The graph axes are simplified at the moment. Don't look at this. And you can see that we can present the same data in two different ways. We can either group the methods together and position each of the compounds separately, or we can separate it based on the method and combine the compounds together. What do you think? What could be the purpose of the left-hand side graph compared to the purpose of the right-hand side?
The left hand is comparing the compounds with less focus on the method, but while the right one is more like focusing on comparing the methods and less on the compounds.
So the left-hand side is more comparing 1 and 2 to each other? Did I get it right?
No, the left one is comparing the compounds A and B to comparing to each other with less focus on the method. So if it's more like, you can see like A is approximately 40 and B is approximately 60, and it's going up. And while on the right hand, you see both have the trend of going upwards, but they are a little bit difference in steepness and.
Yes and no. In this sense, I tend to agree that on the generally you can see from the left hand side that okay, compound A is around 40, but at the same time the left hand side is good to compare. Oh my god, today we are not drawing anything. Okay, I have my drawing problems again, but let me try to do it then in the other way around. So the left-hand side allows us to actually compare method 1 and 2 for compound A quite nicely, because they are next to each other. We can directly see, okay, compound A, method 1 gives a higher recovery than method 2, because they are next to each other. It's quite easy to see which one is higher, which one is lower. And the same for compound P and compound C. On the other hand, the right-hand side can help us to see how does the trend change from compound A to compound B to compound C. But it's kind of harder to compare A for method 1 and for method 2. It's hard to understand which of the bars is higher. So if we want to compare 1 and 2, then the left-hand side, graph is better. They are next to each other. While on the right-hand side, this is quite complicated. They are further away from each other. But comparing compounds is very simple because they are next to each other. So generally saying, if we talk about bar charts, then the things, the properties, the bars that are next to each other are the ones that we aim at comparing when we build the graph. Okay? Okay. So let me show you another example from the temperature change in world for the last 120 years. So the first question I have to you is, what do you think? Which media is this graph now meant to?
The scientific community, I think, like more like those that really need to use the data instead of like the public, because it's like it's not very well present. There's like a lot of data at once.
So the opinion is that it's for scientific community.
Yes, and the result is not very for people that doesn't work with this. This would just look like a weird picture.
Mm. So it would look like a rug or something like that, a colorful rug.
Yeah, something to put on the floor.
And probably
it's not a complicated graph either. You can see the years on the bottom, and then each color corresponds to temperature. So I think anyone that has worked with graphs probably can figure out what it means. So it's not like it's like a graph specifically for one type of scientists. It's like everybody can understand it.
Mm-hmm. Yes, so that indeed it's not very complicated. I completely agree. So we have a timeline down here, which is simple to notice. We also have here the scale of the meaning of the colors. There is a bit of a problem with the scale. Can anyone point that out? What could be bad with the scale?
It doesn't state for the period of the change.
So probably the period is the same, or is the whole range, in the sense that we wouldn't make different scales for different time periods. There is something with the units. We know probably from the title that it's the temperature change that is here, because the title says that it's temperature change.
It doesn't state if it's Celsius or Fahrenheit or anything.
Yeah, exactly. So it doesn't tell us anything about the of the units of these numbers. So that could be, we expect them to be Celsius probably, and probably that's the truth, but it would be good to also have this kind of information in here. At the same time, we can see that there is also another dimension of the information. So we have this y-axis here. We have countries on the left-hand side, and we have the regions on the right-hand side. So we have a bit more dimension than just the time and the temperature change. So it is a bit more detailed than just talking about temperature change. And I think that is actually debatable if this is really for scientists, or is it more for public communication or popular science? In the sense that, as you already pointed out, it's probably not for very specialists because it's not very complicated graph. It only has this one thing, which is temperature, temperature change actually. And therefore it probably fits for either really people researching climate change, but probably not focusing on that super much, or for popular science communication in a specialized column that specifically features temperature change over longer period of time. And probably it is also meant as a written communication, right? Because there are all these countries that are on the left-hand side, which means that there is an immense dimension of this data from this point of view. Now I would like to ask you one more thing, and this would be that when we here on the previous slide talked about the message, do we want to compare the compounds or do we want to compare the methods? So what do you think could be on this graph, the message? Probably there are many in this case.
Comparing the regions as how they are affected by the temperature, like if you check, most countries in Europe are red, as well as most in Asia, Middle East part, while Africa and Americas are less. So it could be said that Europe and Asia are more affected by the climate change.
So indeed, it allows us to compare different regions. So because the countries have been grouped together based on regions, so probably one of the aims is to allow us to compare how is a temperature change in America compared to Europe, compared to Africa, compared to Asia. So this comparison. But even before that, probably it is to show us that the temperature change is going towards higher temperatures. So that's probably the base aim. And then comes the fact that, okay, we want to change, we want to compare different regions. Anything else in addition to this?
You can see like outliers. There's like some in America in the top, they're like the third or fourth row. There's like one that's different than comparison to the rest.
So there is also the dimension of the countries. So a sub aim could be that one could really go to this plot and point out, okay, my home country is here, what is happening with my home country? Or, okay, all these American countries are behaving like this, but there are some which are behaving differently. Why could that be? So showing also differences that may exist in the data set. Anything else? Okay.
The change over time, like if you check 1905, the temperature was going downwards, while nowadays it's going rapidly upwards. You can see that by the color change from blue to red.
Aha. This is actually interesting. Does it mean that it is going downwards?
In the beginning, it's like in the blue area, which is like minus, and then it changes to the red, which is positive, which means it increases, right?
Yes and no, I would say probably. This is now something where I would say that we are kind of lacking this information about the meaning of the colors, or we would maybe need a bit more explanation here by the graph, by the person who did the graph, or the persons, in the sense that expectedly this is the change relative to the mean of this country. So naturally, if it would be just constantly going up, the values on the left-hand side would be bluish, going through colorless, and then going to red and darker red. So if it would be just monotonic. So this, therefore, I wouldn't say probably that on the left-hand side, the temperatures were going down, but rather that they were lower than the mean over all of these years. Did I explain?
Yeah, but as I understood it, it was like the scale down the bottom and like in comparison to last year's temperature, it has gone up or down X amount of temperature.
Well, that's very good when we understand this differently. I don't actually know what is the real meaning of this, because it is a graph from a communicated medium, but this very well shows us how the lack of this small information here makes us understand the data differently. So this emphasizes the need for this information. Any other comments or opinions? No. Okay, so I show you a different graph. This is now again about global temperature, a bit longer period of time. And this is now not for different countries. What do you see here? What do you think now in comparison to the previous graph? What could be the aim?
To show that the temperature has gone from below the medium to the above the medium, but yeah, it doesn't specify how from when the medium is measured, but
indeed. So here the main idea is to show how the temperature is changing over time. So the basic goal of these graphs is the same. However, here we have a bit less dimension in the sense that we don't have the information about the regions and the information about individual countries as we had in the previous graph. So this is probably something that we could grasp also over a shorter period of time. So I could, for example, show this graph on presentation in a conference or in a talk. So that would fit that well. Though regarding the median, I would think that the median is over all of the data points. That is what median normally means, that one takes the median over all the data points put on the graph. Okay, so this is about how to choose, how to present, depending on where you put it. Is it the printed media or a talk? And also, what is your audience? So probably here on the last graph, again, the audience is not very, very experts. Rather, it's more for general communication. Okay, so now let's also look at some technical aspects. How to try to make your presentations and your data very easy to follow. And we will talk about slides, color schemes, fonts, how to declutter your graphs, as well as labeling and annotations. So first of all, when we talk about slides, then slides can be used for basically three different purposes. The obvious purpose that I guess every one of you has used slides for is to present when you are giving a talk, either that being a talk in a seminar, on a course, or being the defense presentation when you are graduating, or I think also in schools you have already given presentations. However, presentation slides are also often used as handouts. So that means that you can use the slides also to send the information to someone who is interested in your research, in your data that you have measured. And these are called slide decks, and they are very popular way to communicate data in startup world, but also increasingly in science and governmental levels as well. And then there are things which are called slide docs, and these are slides which are basically reading documents but prepared on slides. Why would someone make a reading document on a slide, you might ask? We already have Word and we have PDF and we have so many other file formats. Why do we do that? Would do that on slides? And actually the reason is simple. It is very easy to type very long texts in Word files, but slides give kind of limitation, and having too much text makes the information more slow to digest, and also more likely that the text is never read. So slides in the slide docs basically are used to reduce the amount of text that people use. And slide docs are, for example, used when you receive advertising texts, for example. Sometimes you get an email with some advertising text, and then these can be, and very often are, slide docs. But in research, we more often talk about the presentation slides and also handout slides. So let me show you an example of a presentation slide. I don't pretend these to be perfect. These are my slides. I just try to give it as an example what is the difference between a presentation slide and a handout slide. So this is, for example, a presentation slide from one of my conference talks. There is relatively much information. I would say that this is one of the most text-rich oral presentation slide that you normally use. So you can see elements in here. The first element that you can see is that you have a title. At the moment, it doesn't mean much to you. It's taken from a real presentation, but on the conference talk, it would mean something to people. You can also see a relatively short subtitle or some kind of information that gives background to someone who maybe, I don't know, checked the mobile phone or made a note and then turns back the eyes to the presentation. So some kind of small text, but really condensed. Just saying the keywords. It's not really a sentence. It doesn't have the sentence build up, starting with a noun and having a verb and ending with a point. And then you normally have graphs, not sentences, not text, but graphs or pictures or tables. The graphs will look in detail, but you can see that the graphs are not too crowded, let's put it this way. And now let me show you in comparison how I would turn this into a handout slide. So something that you would send to people who were not on your talk and who only see this and they read it on their own. So if I would send that to someone, then I would turn it into something like this. So first, again, there is a title, but the title is much longer now. The title already says what is being showed. So in the oral presentation, the title only said solvent. Probably I was saying something like this when I was presenting this. Oh, now we are going to look at solvent effect on deionization efficiency. But because on a handout slide, I'm not going to be there and telling this story, then I would need to write it down here. It's again not a full sentence, but it conveys what is going to happen. And then on the long sentences, a couple of long sentences, 3-4 sentences, underneath the title, I explain the main findings. So this is almost the story that one would tell when orally presenting the slide, but in maybe a bit more condensed manner, a bit shorter. And then the graphs can be below in the same way, or you can add a bit more details to the ones that are sent in the handouts. And the handout slides are something that you can think of being similar to the graphs that you put to your reports, to your thesis works. So this is kind of the way you would probably find application to them in the near future. Do you have any questions between the presentation slides and handout slides / graphs?
So there's no change in the graphs themselves between the handout and the presentation?
There can be, in the sense that the ones which are in the handouts can be more detailed. You can add here much more details. More questions? No. Okay. So let's view graphs in a bit more detail. The main graph types that we use in analytical chemistry situations. So as I told you before, that can be different when you present, for example, for biochemists or electrochemists. But the main things that are the things in analytical chemistry, and which also most people understand who don't have the domain knowledge, are bar charts or stacked bar charts, scatter plots, and line graphs. And let's view each one of them. So bar charts are this kind of chart where we have different bars, and we can use the placing of the bars to compare different values. Bars can be used to present, for example, concentration, for example, recovery. Generally, it is good if bar is used for something which actually has a meaning from 0 to the top of the bar. So if if this extent in here has some kind of a meaning. So for example, if this is a recovery that I'm presenting here, then that conveys us that, okay, this amount, this portion of the compound is being recovered. So it makes sense to have it as a bar chart. But things which can't be really associated like this might not be the best things to convey in a bar chart. So a bit background in this could be good. Then there are scatter plots, and scatter plots are basically dot plots where you plot where each of your dots has 2 dimensions, the y dimension and dimension plotted on the x-axis. So for example, here I'm showing how did the pKa and the log p-value of a data set change. So how each of the points had which kind of pKa value and log p-value, and I'm trying to say that, okay, they had a short, a slight correlation. So generally in this data set that I investigated, when the log p increased, also pKa increased. So this is something that I would be unable to express in a bar chart, in the sense that I would have very, very many log p values, and it wouldn't really give me any kind of an understanding what is going on if I would be just plotting them as different bars. In addition, neither pKa nor log p makes any sense in a bar chart, in the sense that we can't think of log p as amount in the bar height, for example. So this would be a bit problematic. And bar and scatter plots are mostly useful when we talk about correlations, for example. So when you do calibration graphs or correlation graphs, these are mostly scatter plots. And another thing is line graph. So these are cases where we can put on the y-axis something that is monotonically increasing or decreasing, and we can use the lines to show the trends with this monotonic or increase. So for example, here in this plot, the idea is that we have changed a solvent composition monotonically, and we display how is a method parameter called ionization efficiency changing. So we can connect different data points with a line and have these lines plotted here. When I ask you, comparing the line graph and scatter plot, could I use scatter plot to present the same data set that is now presented here on line graph? What would you think?
Each line means like a different thing. So if you just make its dots, it's going to make it a lot more complicated to see which dot is corresponding to which line, because the line probably is like a compound or something, and then you mix up all of the points and as different compounds.
Exactly. So the fact that we have these lines here almost automatically refers that the different points are belonging to something which is the same. So in this case, this is the same compound. But if we would just use points, it would be very complicated to understand which point belongs to the same compound. if they would not be connected to each other. And then we would basically, what we would need to do is that we would have a graph for each of the compounds. We would not be able to put several compounds on the same graph if we want to have it readable. And now let me ask also vice versa. If we would have this scatter plot where we had these 30 compounds with different pKa and log p values, could I use line plot in here?
Is there any compound double, or is it just all different compounds?
These are all different compounds. They all have one log p value and one pKa value. And yeah.
So it would be very complicated because you don't know from which point to draw to which point. So it's like a million possibilities to how to draw the lines.
Yeah, exactly. So in the case that there is no real meaning or no real ground to connect one point with one other point specifically, it is almost impossible to have a line graph in here. And if we would just randomly connect them, then we would basically get just a big mess where no one would understand what is actually going on in the data set. Okay. Do you have any questions or comments? No. Okay. So let's talk a bit about color schemes as well. This slide is not a good slide to present on a conference or on a defense, first of all, because it has too much text. This slide here, and this actually happens quite often in teaching, that we have something between handout and the actual presentation slide, because we know that you will come back to these slides and potentially want to read them. So the lecture slides are often in between the presentation slide and the handout slide. And this is more a handout slide than a presentation slide. Basically, when you start scratching your presentation and you know what is your audience, you know what is the message you want to convey, then you also choose some kind of style. And the style is a lot based on the colors that you have. The colors in normal presentation, you basically could have two, sometimes a bit more, but basically two colors, a main color and a highlighter color. So the main color is the color that we use in our text and also on most of the drawing axes and so forth. The main color should be neutral. So for example, one good color is black. Sometimes black is too intensive. For example, I find for myself that black is too intensive, so I normally don't use that, but black is perfectly fine. If you want something that is like a bit different from black, then gray is very, very good. Dark gray, not too light gray so that it wouldn't be readable. Or dark blue, dark green, grayish blue, grayish green, also very good colors. And this is what you basically use for all the basic stuff. Then you also have the message in your data. And this message really needs to pop up. And for this message, you would use a highlighter color. And this, of course, needs to match with your main color, in the sense that when you use black or gray, then that's not very hard. Almost every color fits. If you use gray blue, then you might not want to use some particular tones of color. So should fit, and it should be the one that really highlights your important messages. So you can use that to highlight keywords in your presentations, also the most important numbers and most significant data points on your graphs. Okay. And sometimes you also have a second highlighting color. So this is when you want to show contrasts. So for example, when you have maps or time data, like you saw in the temperature graphs, then you might want to have two colors that you use for highlighting. And another thing when you need to have actually more colors is when you have a dark background in your slides or on your figures. So in case of dark background, you probably want to have a base color that is light, as well as two highlighter colors. Yeah, so I received in between a question about the break, and I would say that we make a break in 15 minutes. We have a couple of slides to go through, and then let's have a break. Is that fine? Okay.
Yeah, that's fine.
Cool. Thank you. So let me show you how this color, highlighting color could work on graphs, for example. For text, it's, I guess, quite easy. So here is an example of a recovery investigation for 5 methods, A, B, D, E, F. And the recoveries have been plotted as bars. And the desired recovery is between 80 and 120, actually, not 70, I'm sorry. And the highlighter color can here be used to highlight the method that performed the best, that you choose, that had a problem, something that you want to highlight. You can do the reasoning with your vocal expressions when you're presenting, but the color you can use to actually draw the attention to, this is the bar that you should focus on. If you are presenting on written media, then you could also add a bit of text on the top of your graph, for example, why this is the highlighted color. And another example about time series. So the concentration of 3 compounds has been investigated over time in environmental samples, and we could do this as a line chart, and then we have the one compound highlighted, and it turns out that this is the compound for which we can see an increase in the concentration. So this compound B sticks out from the graph due to this color highlighting. Okay, questions about the colors? No. About fonts. Also, fonts can be quite important. A text, all fonts are the same in 12 different fonts. My question to you, are all the fonts the same? Probably not. No, probably not. You can see for...
You should probably focus on which is more visual and that everybody can read it easily. For example, there's that one that looks like an A lying sideways, almost the 4th from the bottom, which is maybe not the best for a scientific article because it's not that easy to read, and unless you're used to it, at least.
Mm. Yeah, so
Also,
the
some of
yes,
them are playful and some of them are serious, so it could be for different content.
exactly, yes. So some of them are hard to read, some of them are easier to read, some of them are more easygoing or playful, like for example the third from the bottom, while some of them are more conservative, and some of the fonts also have they already convey a kind of meaning in the sense that what this text is. So, for example, the fifth from the beginning, this one, does it associate with some of you, for some of you, with something?
Newspaper?
Sorry, I didn't hear.
Newspaper a little bit?
I still didn't hear, I'm sorry.
A newspaper.
A newspaper. I think can be as well. But this is also something which for quite large audience associates with code, with writing code, or with different programming languages, as well as just mathematical way of writing. So if I see something like this, then I would expect this to be basically a code. And even the ones which we wouldn't maybe associate with something are a bit different. So for example, let's check this one over here, which is the sixth from the above and the seventh from the above. Do you recognize them automatically? I think you have seen them quite often, probably. Some of the very common fonts. So the sixth, this one, is Times New Roman, and this is Arial. So two of the probably most common fonts in scientific writing. And interestingly, and actually quite sadly, Times New Roman was a very often used font for a very, very long time, but it's actually quite hard to read. Let me explain you why. Here are two fonts. These are Arial and Times New Roman on the left-hand and right-hand side corresponding. When Arial is a sans serif font, then the Times New Roman is a serif font. And what does this mean? This means that the serif fonts have these tiny little extensions on the letters. You can see this here, and you can also see this outreaching part here, this thing over here. So all the small details in each of the letters, these are called serifs, and they make generally text harder to read. So at the same size, you would basically spend more time reading the text with serif than the one without serif. And serif is okay in printed press, even though this is also reducing now. But on presentations as well as web media, we generally want to use the sans serif fonts so that it would be as simple as possible to read. So Arial is one, as well as yeah, there are quite many. that are, I would say that today most of the fonts are sans serif fonts actually. And what is also maybe important when I go back is that all of these fonts are here plotted actually at the same font size. But you can see that even in spite of the same font size, they are actually looking differently large. So the size of your font also depends on what is your font so that it would still be readable. Okay. And just this one same sentence in Arial and in Times New Roman, it's quite short and maybe it's not so striking, but generally serif fonts are a bit harder to read. Okay. Font size, as I told, depends on the font. The serif fonts, if you need to use them, generally need to be a bit larger, and some serif fonts can be a bit tinier. The general thing is that it needs to be readable. Ideally, if you're giving a presentation, then you would like to know what is readable in this particular room that you will be presenting. So, for example, if you will be presenting your bachelor thesis work in one point, then it's good to go and test in this room, on this screen, what is readable from this particular screen. Then in addition to the general size, it's also important that the font size would be the same on the slide, meaning that you should unify the size. All the slides should have the same font size. So not that one slide has 16 and the next one has 20 and then the third one has 24, but that it's always the same 20, for example. Also, try to unify the font size for your text and for your graph, meaning that also in your graph, all of the text would be of the same size. It makes the graphs much, much more readable and also looking as someone would have actually thought through when placing this data. Larger font can be used for title, and is often used for title because you want the title to stick out, and also some for the subtitle if you use that. So for example, in this slide, the title has a larger font, the subtitle has actually the same font size as the general text, but they are of different style, and then all the text has the same size. And this font size is already related to another important aspect of doing presentation, and this decluttering. And here really less is more, in the sense that if you can rip off parts from your graph that are not needed, then this should definitely be done, because otherwise the readers or the listeners will be lost. So again, think what is that you want to say. Does this graph fit this purpose? Is there anything that is not important? If there is, remove or change the color more neutral if you really want to have it in the background for whatever reason. Try to use the color to make it less visible. And use a highlighter color to show what is important on your graph. So for graphs, that would mean that normally you want to remove grid lines because that causes noise on the graphs. Generally have the same color for all of the axes and have this color neutral, your base color basically. Label axes with units, but put them in an orderly way, and align axis labels as well so that they would be either in the center or on the end of your axis. Then for line graphs, use line markers only for the most important points. So generally you don't want to have the line markers. There are some exceptions when you want to do that, but this is then for highlighting the most important point. And for scatter plots, what is important is that the axis should be scaled. That means basically that if you are plotting, for example, measured versus expected values, then you want them to have the same range as well as the same size, so that it would really be proportional and scaled. Okay. Do you have any questions? This was very fast and very many things. No. Okay, I'm gonna pass by the next slide. We are going to look at this after the break. And then I'm gonna talk what that slide is about. But just before we close, another aspect is aligning. So aligning is very, very important. Aligning means that all of your, if you have two figures, for example, on top of each other, that they would be aligned also, for example, to the left, and that they would occupy the same dimension in the sense that one would not be longer than the other or somehow out of the measures. And in Excel, there is a, under format, there is a very good tool, Align. Make yourself familiar with that when you're starting to do first presentations. This helps you a lot to make your presentation look more compelling, I would say. So in addition to the same size of font, also try to make your figures and your tables of the same size. If you have two figures, make them the same size. It reduces the noise of your graphs a lot and allows people to focus on what is actually displayed on this graph. To this, if you're doing the graphs yourself, then you can make them from the beginning in the same size. If not, use resizing, cropping, cutting, all these kind of tools for that. Align the items that you have, and if you have single item, then having it in the middle and in the center is quite important. Otherwise, if you have more items, then usually align to the left is what people use. But the most important, that it is aligned. Play around with it yourself to see how it works. So an example graph about aligning. This graph is very, very bad. I'm showing you a very bad graph. There is nothing aligned on this graph. This is not how to do it. So what does it mean that it's not aligned? First, I have here 3 photos, and they are each of a different size. How would I need to redo that? What do you think? To make it a bit more organized.
rescale them, like zoom or pull the pictures, like you can do in PowerPoint. You can make the pictures bigger or smaller.
Mhm.
Then you can cut them as well if needed.
So basically, I would first need to resize the bread picture and the computer screen picture so that they would be of the same size. Then I would align them so that they would be on the same dimensions in here. And then I would also need to resize the map so that the map would not extend further than is the upper computer screen picture, and also not beneath the bread picture. And last but not least, I would need to make sure that the map is also of the same width as is my computer screen and bread picture. You can see that. Okay. And labeling. Well, sometimes we need to add labels to the graphs as well. And it is not by far needed for all data, but for the information that is most important. So let me show. Okay, hello, welcome back after the break. The last thing we were talking before we went for the break was about labeling graphs. And let's see now some examples. And before we actually get to an example of labeling, I have here a bar chart, which is about the recovery of a compound with the sample preparation methods, 5 different methods. And I'd like to ask you, can you point what is wrong in my graph? There are several things.
No units.
No units, or even more, not even any labels on the axis. So probably I would need to put here something like what is it? That it is a recovery. And I would also need to put the units there. For example, in square brackets or in round brackets. Round brackets more often. Or with a comma can also be. Depends again on the convention of it. And probably I might want to also write here that this is a method. This now depends on how am I going to present this. So if this is written communication, then I would rather have it. But if it is a oral presentation, a talk on a conference, and I'm talking about these 5 methods, then it might not be necessary. Okay.
Standard
yes, very good.
Derivation.
Sorry?
The standard derivation.
Aha, so there is no information about the repeatability or standard deviation. So I would need to add some error bars here. Everywhere. Yeah. Anything else?
Yes, we don't know why is C missing.
Aha, okay, maybe there is some reason for that.
It's quite misleading that the recovery scale goes from 40. It makes it look like A has nothing.
Exactly. The scale is completely wrong. It should start from 0. This is a typical Fox News graph, in the sense that Fox News is famous for having graphs which start from a random point just to give an impression that something is very large or something is very small. A normal bar chart starts from 0. Anything else that pops to your mind?
A C-bar.
A what?
You have A, B, and the C is missing, or does it even matter?
Yeah, that's now a question. Maybe there is a reason. Maybe there wasn't a method that was labeled C. But this is a good question. Should there also be a C?
Our experiment might have excluded C, so that could be a reason. Like this is the second experiment in the lab.
Yeah. So there, if that is again a written communication, then maybe somewhere on top of my graph I would write why C is not there. And probably I would also write what are A, B, D, E, and F in a bit more precise way. Anything else? Actually, I'd say that this is very good, pointing out that the labels from the graphs were missing, the units from the graphs were missing, that the start of the y-axis was completely random, and that there is no information about the repeatability, which could be there as should be there as well. So based on the same graph, let me show you now a bit modified version. The Y scale starts now from the 0, like it should. There is recovery said in here, and there is also percentage. And here I show you how you can add values of the bars to the graph if you want to. So for example, maybe it is important to display also the numerical values, and then you could include them on this graph. Maybe you don't also want to put it for every one of them. Maybe you just want to put it for one, then you would just have it on one and maybe not on the other. This kind of a possibility. And for example, in the top, I have a mistake. The desired recovery is 80 to 120, I'm sorry. But if you, for example, also want to show this desired recovery range or acceptable recovery range, then we might add to our graph another feature to add a small range where the acceptable recovery is. And then it kind of becomes also obvious why we have highlighted the extraction method D, because this is the one that reaches our acceptable recovery.
Also fit the requirement. If it's
I have a mistake in the head of the graph. It should be 80 to 120. I'm sorry. I have a typo.
And how can the recovery rate be 120% when you 100% is if you get everything back, so you get more back than you originally had?
Yes, that's it sounds not correct, but that is how the official regulation is for some of the methods. So for pesticide analysis, the official limit goes up to 120. The reason being that some of the pesticides that are monitored are transformation products of the other pesticides. So it can be that if the two pesticides are present in the sample together, then one of them degrades in a very small amount, but in the end, the recovery of the transformation product is a bit higher than 100%.
Okay, I understand.
Yeah. So basically it is said that it should not increase more than this 100 to more than 120. Okay, so this is about highlighting and adding labels for bar chart. When we look at the line chart, then we had these 3 compounds that had been measured on different from environmental samples over longer time period. And here, if we want to, if it's important, we can also highlight some numerical values. So for example, maybe we want to show how much has the concentration of compound B increased over time. So it started with 12 nanograms per liter, but now it is 72. So we can highlight the start and we can highlight the end. And then we also use this marker in here, so this small dot in here to show what this value, where this value belongs to. But we don't need to put it for all of the points, only the ones that we want to draw attention to. Okay, questions? No questions. Then I also want to tell you about different tools that can be used. The main rule about tools is that use the tools that you know how to use. And this is not only about doing presentations and doing graphs, but in general, in preparing anything at all. Use the tools that you know. If someone says, oh, that's a very fancy software to do graphs, then first think how long it would take you to become familiar with that tool. And if you have a tool at hand which can do a very good thing on its own, then it's a matter of weighing the pros and cons. The ones which, so this is not an exhausting list. These are just some of the things that you can use. I think most of you would prepare quite many of your graphs in Excel, and Excel is very good because it's almost everyone has it. You can do it also in Google Online Excel templates. It's very simple, it's very accessible, and actually absolutely everything can be done. It's sometimes a bit of workaround to get everything done, but everything can be done. The downside is that when you do it once and you need to redo it basically on very similar data, then you actually need to start from scratch once again. So it's not very well, you can't repeat drawing the graph on new data very easily if the dimensions somewhat change. If you feel comfortable with programming languages, then the tool to use today is in our language a ggplot, which has very wide options available, including interactive plots. So plots where you can actually, where the user can zoom in, the bubbles can change, can move on your graph and so forth things. And it is also very easily applicable to several data sets. So if you want to do it today for 10 data points, but tomorrow for 20 new data points, then you don't need to start from scratch, but you can just run the same code to do the new graph. Yeah. And if you are not only doing data, but you also want to add some illustrations, then Adobe Illustrator, for example, can be a very good resource, and it's really, really very beautiful, the things that you can do there. The problem is that, at least for me, is that its entrance barrier is quite high. So I still feel that I'm learning how to use it. Maybe you have used something else. Does anyone have something that you use and you feel that it's really good tool that you want to share with others?
I usually draw graphs in MATLAB, but that is only because Excel doesn't have a graph option for tablets.
Aha. Okay. I didn't actually know that.
I haven't gotten it to work in app form, at least.
Okay. Okay. Should check that out. I usually don't use Excel in the tablet, but it's a good point. Okay. Do you have any general questions or comments at the moment? No. Then I maybe want to show you something ugly. This is a slide which is from my master studies time. It is very, very awful. And why I want to show you this to you is that first of all, no one is perfect and all graphs can be improved. When I was researching and going through to some of the, looking for different graphs and from different presentations, and I found that graph from my own old presentations, I felt very ashamed of having being done this graph. But then I thought, okay, this is a good possibility for you to point out what is all wrong on this graph and to use this as the basically worst possible example. So I'd be happy if you could help me pinpoint absolutely everything that I have done wrong on this graph. Does someone want to start? I don't feel any bad. No, I'm very happy if you find things that are wrong, not the other way around.
It looks very cluttered with all the markings at every value, instead of just having different colors, for example.
Then all these things should go from here.
Yes.
And the solvent, why is it like every other is like 80-20 and 60-40?
So that's a bit complicated what is going on here. Maybe it would be better to split the graph into two parts, just to have methanol on the right-hand side and acetonitrile on the left-hand side, and then just have a percentage on the x-axis of, for example, formic acid solution.
It is also very bright colors, which is not easy to look at.
So there is definitely more than two colors on this graph, and these colors are not, they are too intensive.
Then there are
I think we don't hear you.
there's dots on all lines except of two, which makes it a bit weird that everything except those have, like the dark blue and the light blue line.
Yeah, yes, actually there are, but they are so poor that you can't see them. But generally, we could kick all of them out. We could keep just the lines. Anything else?
There are also 2 lines that just end, which is shorter than the others, and no explanation why.
Yeah, so there are 2 which are only available for these 2 left-hand side measurements, and they are not on the right-hand side. So first of all, there is no explanation. Maybe if we would be talking about this graph, then we would explain that. Or if that would be a written slide for written communication, then we would need to write it down somewhere up here, why that is missing. It becomes visually a bit less problem when we divide the graph into 2 graphs, one for acetonitrile data and one for methanol data.
The label on the y-axis describing what is measured.
So there is, but it's kind of cryptic. So it's not really explanatory. So we might need to rephrase it.
A title.
A title. Yeah, let's. That is a slide, so that is our title, but maybe it's not very explaining.
Doesn't the diagram need a title of its own, or?
Yeah, so diagram or a figure on slide doesn't need a title on its own. If the title of the slide is explanatory. But that's definitely true that the title is a kind of cryptic in here. Anything else? There are at least 3 things. 4 things.
Maybe that the lines are unnecessarily thick.
Yeah, okay. They could be thinner. Yes, that's true. Some more.
The bottom line is like you can't see if it goes above or below, or if it's just lying on 0.
So where is this compound really? So it would need probably to extend this y-axis a bit further to see if it is actually going below. What do you think of the numbers on the y-axis? There is a problem with them. They look generally okay when we are in Swedish communicating. In English, we would actually communicate them with point. So we would communicate 4.5. But even if that slide would be in Swedish, there is a problem that some of them have 0 decimal places. Some of them have 1 decimal place. So that should be fixed. They should all be in the format of 1 decimal place. Then something else, does something come to your mind still?
Maybe the grid lines.
Yes, the grid lines have to go. One more thing which is very similar to grid lines are the boxes, the box of the graph. It's just unnecessary noise. It needs to go. Anything else? What do you think of the legend? There are two worries with the legend. These are compounds, but do you understand which compounds they are? What could be 2Na? And I think this is actually simple out of the ones that we have here.
It's difficult to recognize the name of compound.
Yeah, exactly. So these should be substituted with the real names, or at least some kind of an understandable presentation of the compound. So we could, or if not write systematic names, then at least recognizable names. So for example, this would be methylbenzoate. So we would. And so forth. And another thing, of course, the legend doesn't need a box around it. And it would be even better to add these labels directly to these lines. So we could skip the legend altogether by just writing the text over here next to the lines. Okay, is there anything else?
Was there anything in particular that you wanted to show with it? Like, is there any purpose that you want to highlight that isn't highlighted?
Aha. Yes, so there is nothing really high, or there is absolutely everything highlighted, we could say in here, because all of the compounds are really, really very colorful, as it was already said before. So there is nothing that is really highlighted. And this is something that could be changed with the colors. The question is, what do we want to show? For example, if we could want to show that when the percentage of the formic acid is increasing or is decreasing, then this compound goes there, or that compound goes to another direction, then we could highlight these compounds. So that now really depends on what we want to highlight. Or actually, if we would, for example, want to highlight the difference between acetonitrile and methanol, then we would actually need to regroup the graphene all together so that we would have the same percentage of acetonitrile and methanol next to each other. And then we could highlight there the differences. Okay, anything else? No. Okay. Let's go to some more training. This we are not gonna look at.